Hello everyone and welcome to another Würth Elektronik webinar. Today's topic is connector temperature rise and derating. My name is Markus Eberle and I will moderate this webinar today, and I'm very pleased to welcome Götz.
Hello Markus, how are you?
I'm good. I hope you are doing good as well.
Excited, of course.
Thank you very much. So as you can see, Götz is working as a field application engineer at Würth Elektronik, and he will hold today's presentation. So before we start the webinar, I would like to point out a few little things. So first of all, you are muted in this webinar, so if you have any questions, you have the possibility to ask us the questions with the Q&A function in the webinar, in the WebEx function. You will find that on the lower right-hand side. So then the presentation will be about 30 minutes long, and after that we will also have questions for your time for your questions. So we will wait until the end to answer your questions. Also, if you have afterwards any questions, please feel free and just write at webinarteam@we-online.com. So then also just a hint, if we will finish, and when we are finished, we will record this session and we will then send you the link to the recording as well to the presentation for you to in the next few days. So then that's all from my side. I wish you a very good webinar, and yeah, stage is yours.
Thank you, and thanks for a nice introduction. So welcome everybody here online. Yeah, nice you're all joining. And today's title, is about derating and temperature rise, which happens inside of a connector. And therefore, we will step directly into the topic. So there's a bad image. Everybody should get goose pimples if you see that kind of picture in your near environment. And this is a true picture we received from a customer with one of our connectors, but not because our connector was not able to hold to withstand the current. Of course, it was a failure in point of temperature. That means we had too much current on this connector, and therefore it got too hot. And the bad thing was that this was inside of a closed box, so there was no possibility for the heat to disappear, and therefore the temperature rised to a higher point as this connector could stand. Yeah, and to avoid things like this, even if they are not drastic like that, but this is our topic today, how we can gain this and what we have to watch out for. So here's a brief look into our agenda. It's about the design of the connectors in terms of electrical current. Then, of course, what happens if you see a too high temperature. Take a look at the temperature rise rules. There are some standards out for this. We look at how heat is dissipated and how you can get rid of it. Then, of course, what is the heat in the cable? We have some tricks and some observations that we did for you. We look to a derating curve, how we can find the relevant information there. And at the very end, we have our connection horror show. So let's start right into that topic. So here you see some connectors that you may know already from our portfolio, or that you already have on your PCB or equal types. And on the lower right-hand side, you also find an extract of the datasheet, which tells you its operating temperature should be between -40 and up to 105 degrees Celsius. And also marked as the current rating. We don't care about voltage and so on right now. The current rating here is given with 20 amps for UL. And now the question is, if I look to these data, 105 degrees, can I run this kind of connector with 20 amps at 105 degrees? And this is a question we will find out later. So if we look to a connector could also be seen as a resistor. And as we all know, a resistor which is running, or if a current is running through a resistor, yeah, of course, it will heat up. So this means you will gain some temperature rise. This resistor is getting warm, and looking to your ambient temperature, this room temperature normally, during the operation, this kind of connector should not overheat more than 30 degrees plus. Following the UL standard, there are other standards out there, like the VDE, for example, but the 30 Kelvin temperature rise is something that we have to look closely on. Yeah? This kind of, you see on the right-hand side, the image of a heater, electric heater. This is exactly the principle what this heater is using. It's the so-called Joule's effect. So this is happening anyway, and in some way we need to get rid of the temperature in our system. So we have done a lot of tests and observations to find out how is this, apart from all the theoretical view, now to find out how does that act in natural. So you see here on the left-hand side a connector, a very traditional connector, and we wired it completely to run the current through it, and inside we placed some thermocouples. You can see the wires in here going inside here, the red and blue one marked, so we placed that right in the middle, which is expected to be the hottest point of this kind of connector. On the middle image here, you see how we wired that in total. So also the length of the cable was chosen by the standard. So the standard says it has to be at least 50 centimeters long, and the current should run through this connector is always the same current. That means we did loops running through each one of these poles, so it's equal on every pole here. And then, of course, you see the connectors going to the power supply. So what was our observations on this part? So looking on it with a thermal camera, we can see this kind of image. You see where the white spots are. This is the hottest spot, and once again the gain is that the target is that we should not exceed a temperature rise more than 30 Kelvin. And what happened to this system here, we found out we're stabilized running for a while. This ended up with a total temperature of 46.5 degrees, where we had an ambient temperature in the lab at 21.7 degrees exactly. So the delta T, the temperature rise, was just 24.8 Kelvin, which is exactly in the range. You see it's below 30 Kelvin. And therefore everything is fine with that kind of cabling here. And so the question then is, what is the consequence of a too high temperature? Yeah, we saw the image in the very beginning, and What else can happen, of course, is that if a electrical conductor is heated up, it also increases its resistance. That's just by nature. Increase of the temperature also means increase of corrosion speed, especially if you have a very humid surrounding, or maybe some other substances around of the connector. So corrosion speed doubles at each 10 degrees. Yeah? Then, of course, if you go too hot, your solder joint may degrade, or in the worst case, it gets desoldered itself from the PCB. And of course, we see the plastic around of the connector, which is very common, of course. And the aging of the plastic is going to accelerate drastically the higher the temperature rises. So at the end, it turns brown, like you can see here in the picture, or it just gets is getting brittle, or is breaking very easy. Inside also the metal can be harmed. Yeah, we call it relaxation. That means if you have a contact pair where you need to have a spring effect, and then the spring effect may be gets loosened. Losing the force, the spring force, would of course mean that you have an increase of the contact resistance again. And higher contact resistance will, of course, generate more heat. So you have a kind of a devil's circle here, yeah, and heating up to an unclear point. So we can look to this table. There is a formula called Arrhenius equation, and this is looking especially on the lifetime span for all the kind of components, and at the end, of course, to the whole product consisting of a lot of components. And we start at the ambient temperature, generally at 20 degrees. And by the way, if we look to a data sheet, all the data given here also is looking to the is related to the ambient temperature in a laboratory about 20 up to 25 degrees. Yeah? So everything that you can read in a data sheet is relied on that. So if you look to that curve, it's clear that the rise of the temperature will limit or cut down the lifespan of your total equipment dramatically. So if you go to 60 degrees, you see it's divided by 11. And if you only go 10 degrees higher, then it's already divided by 20. So this is, of course, very important for you to understand if you want to build a very reliable component or appliance. Then you should look out to keep the temperature generally as low as possible. So we look to the temperature rise rule once again in the equation here. So if we look to that, P is power, R resistance, of course, and I is the amperage, and of course the current goes into this formula in square. And this is a very important information for you. At the end, it means that if you double the current, you will end up with 4 times the temperature. The lower formula here is for the delta T, and there is also incorporated the constant of the material itself, yeah, whether if you use copper, aluminum, or whatever kind of conductor. So this is what you should keep in mind. And if you want to calculate this, once, of course, you have to measure. And this means we're looking to a system where we do a measurement about E1 here given at 15 amps, and we find out the temperature rise. The delta T is 15K. So if we then want to calculate another type of disconnector, another polarity, then we can easily calculate this. And also, if we want to rise the current, this is the formula that you see here on the bottom. If we rise the current to 30 amps, then it's delta T2, and we end up here with 60 Kelvin by the calculation, and this will tell us exactly what we mentioned, 4 times 15 Kelvin, so it's 4 times the temperature. And this is good to understand, of course. So this is what we should keep in mind. And now we wanted to verify if this information is really true, and we tried to confirm this by the same connector. We did the temperature rise test at 20 amps for this, and we found out that this kind of line here that you can see in the table on the right hand side. So this was about the what we found out, and the red line is exactly the measurement. So this is telling us that the calculation is pretty close to what we found out at the true measurement. And even the true measurement on the red line here is a little bit, you see it on the right hand side, is a little bit below of the black line, which was the theoretic calculation. So this gives us also a security margin. So now we're going to look at how heat evolves, and we can compare this with a sort of tank filling. And what we see here in blue is not water, it's symbolizes the amount of heat, the amount of energy flowing into maybe a connector. And it's flowing in, and on the bottom side it's flowing out as well. And maybe the valve on the bottom is not as big as the incoming amount of heat. So this tank slightly is going to fill up, and we have a curve like this. And even if during the level is rising in the tank, then the pressure on the bottom valve is increasing, and therefore the throughput is also increasing. And at the end, so the curve is flattened, and the ideal or balanced type is the amount of the incoming energy is the same amount like of the outgoing energy, and so the system is balanced and stable. And you should achieve this within a time of 10 to 15 minutes. Looking to an electrical system, because if you don't, if the valve on the bottom or if the heat can't disappear, then of course your tank will overflow, and your line here goes infinite. You're undefined. You don't know where it's going before the connector really breaks. So how heat is dissipated? Of course, you know, on a fireplace, you sit there in a frosty night, turning your face to the fireplace, and you know, you're hot in the face and your back is cold, then you have to turn around. So this, what you feel, is the radiation. Then we have the convection. Everybody knows that heated air is going up. It's going to be lighter. On the top, it's cooling down, and it comes back to the ground. So it just goes more or less in circle. And number 3 is the type of conduction. If you have a massive material, then of course you have kind of conduction that leads also the heat to somewhere else. Remember your frying pan, yeah, with a metal grip or with a hot wooden grip, yeah. So you can decide yourself which one you would touch and which one not. So looking on a PCB, which is undercurrent, yeah, we see the same effect here. All these points, like inside of the connector or the point where the pin goes into the PCB, every single point of that is kind of resistance and all collected together to a global resistance. Yeah? So how the heat can disappear here. We heard about conduction, so this is going through the cable. This is very important to understand. So the copper cable usually is taking away a lot of heat, and the conduction in the FR4 or in the PCB material, which is typically FR4, also is taking some of the heat away. And especially on top, we have the copper layer, and the copper layer exactly is giving away a lot of heat. So this really helps if you have wider traces, yeah, to dissipate the incoming heat here. So you see, we have all the things. We also have the convection, because when everything is warmed up, then of course the air will also be heated up. And if you put your hand on top, yeah, then you also can feel that the radiation is there, that feels hot, and this is exactly what the infrared camera also can detect. So this is the way how it evolves. So heat in a cable is also important to understand. I already mentioned. So we did a test, of course, once again, to understand what is the temperature rise if you have connected a wire. Now, first time we tested with AWG cables, following the standards of the American wire gauge, and we did it with a cables of 50 centimeter. Then we placed 2 thermocouples right here. You see where the wires are going directly to the cable. So the isolation was removed, and the thermocouples were directly connected to the cable to get exactly good results. What is the heat coming up here? So then, of course, we looked at it with a thermal camera again, which is the most convenient point to understand this. The thermocouples themselves, they give an exact temperature of the spot, and they are more accurate than the thermal camera, of course. But here we see the whole image, and we see that the most temperature is on the whitest spot here, which is inside of the connector. But now we're looking on the cable, which is red everywhere. It's just white here and showing like it's hotter here because the isolation has been removed. So what's important to see is the table on the right-hand side. If you look to the wire size given here in AWG, maybe referring to the going on back. Referring here to the AWG 16, which is allowed to go to run with 10 amps, and the delta T should be around 7 Kelvin. So now in the next point, we look at the same same type of connection. So we did it with different type of cables, like from 12 AWG up to powered with 20 amps, and we had this kind of TBL with the 3 poles and the wire length. We changed, and we had 2 thermocouples here, like before. And what the camera showed here, you see we have a 2.5 centimeter in between. So these bridges are very, very hot, as you can see. And the outgoing cables on upper left-hand and lower right-hand side, they are more red, which means they are not as hot as these bridges. So the general question was, how long should the cable be to draw as much energy out of the connector as possible? And this is what we can see here in this little graph that we found out. So if you look to the length of about 10 to 15 centimeters there, the dissipating effect of a connected cable is the highest so far. So we can keep in mind that optimized length is 10 to 15 centimeter. Less, of course, will increase the temperature of the internal connector, and sometimes also over the 30 Kelvin. But if you use more, it's not really helpful in terms of thermal dissipation. So of course we have done some more tests, and we were looking on this kind of connector with only 3 poles, but then also increasing the number of poles with the same type of connector, and different cable sizes and so on. And now the question is, should we decrease the current if you increase the number of poles that we are using? And if you calculate this point, then it's very likely that you end up with a temperature, if you look here to the calculated type, at 12 poles. If you go up here, then we end up with 100 degrees or 100 Kelvin delta, delta T, or temperature rise, coming from ambient temperature of standard 20 degrees, we would end up with 120. So this would be far too much for this kind of connector. And yeah, but how realistic was that? So what we found out really is that in reality, at the number of 8 poles, this was a kind of special point where we found out that the temperature is not rising any further, and even the temperature rise from 3 up to 8 poles was not really significant. So at the end, this means that we can trust the formula, of course, which brings us always on a very convenient side of the temperature development. So that means also we have a good security margin, and we can use the given information on the data sheet for any number of poles. Of course, some data sheets tell you something different, but you're always on the safe side then. So our next test is showing a kind of connector with some wiring. You see this, and it's inside of a closed box. It's same cabling like before, and also we put some thermocouples inside, and we found out here that the heat is very drastically, it's heating up very much. And because there is no real heat dissipation, this is a plastic box with a polycarbonate top cover, so we can see what's inside and look to it with a thermal camera. but at the end it means there is no dissipation of the heat possible. And one of the most critical points is that the system could not be stabilized over a long period. So this is something that really needs to be avoided. Yeah? So we can follow this, and if the thermal energy is stored in the box, yeah, then you really need another way to exchange this. So to exchange this, we found the possibility of putting in some holes into the enclosure. So we have some kind of airflow, and the dissipation should be running over these holes. And we found out, of course, that this was a slightly better solution, and even it was not really good in terms of temperature development, but it ended up with better stabilization. So at least we were able to stabilize this kind of system. So maybe we should have put the holes on the top, so heat is going up. Maybe that changes something else. At the end, this kind of dissipation formula is absolutely cost-free, but nobody wants to have a hole inside of his box, maybe. Yeah. So it depends on the application. So next point is that we, very similar to the first one, but now you can see that we've drawn the cables out more of the box, possibly in the shortest way. And this was again with no holes. And so we ended up here with a very stable system, and we could draw a lot of energy out of the system just by leading the cables out on a very fast path. Yeah. So this is good learning at the end. Yeah. So the external wire, they add the conduction effect, because this is drawing out the heat of the system. And it's even better than holes in the box. Of course, you can apply other possibility for cooling down, yeah, but inside, and the first important thing is that the connector is not overheating, as we learned, and this is at least the best of these three choices that we had. Now, of course, a better way is to decrease the current. If you limit your current, then remember the I square. Or the current goes in the square factor. So if you slightly decrease, then your temperature will decrease even more. And another possibility, of course, is to use thicker wires. So at the end, a cable, of course, needs to be connected to a full kind of system. So at the end, with a PCB, and you can see this PCB here with a power clamp on the right-hand side, and also on the left-hand side a screw clamp. Yeah, we have a 4-layer with a 70 micron thickness, and the trace was 21 millimeter wide. So we run 100 amps over this, and it got warm, of course. This was to expect. And now you can see in a horizontal placed type, we achieved 76 degrees, about that. And now we wanted to understand if we change the position of the PCB to vertical, so the airflow can be improved. And even by this cost-free task, we could lower the temperature even here by almost 7 degrees, yeah? Which is significant for a thing that costs nothing. Of course, you can also use a fan. We have also the different here, a horizontal or vertical type. So horizontal, we ended up with 56 degree, and here 58, so this is only slightly higher. But of course, a fan means you have additional cost and you have additional power that you use for your appliance. So what to remember is, of course, that vertical position is a natural cool down effect. And if necessary, of course, you can use a fan. So we can look to the derating curve now. The derating curve normally is given to you from the supplier with for every component. Now we look to the maximum connector temperature which is allowed. Then we have delta T limited to 30 Kelvin if we are following the UL standard. And we remember once again that delta T is proportional to I square. So this is a kind of connector that we have in our portfolio. And here once again you see a extract of the data sheet where you see that operating temperature is up to -40 up to 105 degrees at a current rating of 7 amp. And you remember the question from the beginning, can we really run 7 amps over this kind of connector if it's 105 degrees hot already? So if you're looking to this kind of derating curve, you maybe wonder why this is flat on the top. It's just because of the cable which can be connected here. The cable in this square is limited in its amperage, and therefore the line was cut here. Normally, of course, you could draw this completely to the top. So if you're looking to this, we see that the operating temperature is going up to 105 degrees. So we use the scale, which is ending here at 105 degrees. And now we want to run as much as current over this. And maybe given that we have a surrounding of 90 degrees, what's the maximum power that we can run over this? What current can we really apply to this? So if we look at this, the maximum temperature rise given is 100, or the maximum temperature of the component is 105 degrees. So you have to deduct 30 Kelvin of that. So you will end up in this area for a surrounding of 90 degrees. Then you can use this up to a maximum of 70%, which is 4.9 amperes for this type of connector. So same thing with another connector. This is going up to 120 degrees, so we have to choose the 120 degree scale again. The cable is limited once again, so we want to find out. And what's good to see here is that you see two different type of current ratings. You see one for UL and one for VDE or IEC. That's equal. So of course, if a connector can be hotter, and this is what we see here, a temperature rise of 45 Kelvin is possible here, then of course you can run a higher current on that. So same thing that you want to find out what current you can run. So at the maximum of 90 degrees, so you would have to limit your current down to 88% of the total one, which is still 21 amps. So as promised, here's a little connector horror show. You saw the one in the beginning, and we did some more tests on that, which meant this MPC4 connector type in 4-pole normally is limited to 9 amps and a maximum temperature of 105 degrees. And yeah, we did almost 4 times the nominal current on it. And yeah, as you can imagine, we ended up with a high temperature. We saw that within 10 minutes it raised almost a marking of 260 degrees. The nice point is that it just melted, and of course it got hot, but there was no ignition of fire. And none of our components that we have tested ever fired up. So this gives me, as an outside salesperson, also the very good feeling about the components, and so you can be really on the safe side here. So the worst thing, of course, as you can imagine, is if something flames up. So this brings us back to the initial image, and yeah, you have to watch out what you do in terms of heat development. Of course, there's other possibilities how you can cool down your whole appliance. You always have to look on the whole appliance, then you can create your own derating curve for the whole PCB. Yeah? And yeah, if you have any questions about this topic, then feel free to contact us, your local sales person in your area, or the field application engineers. And also about derating, we have a nice application note on the web, which is free to download for you, which is really helpful. And beside that, or in addition, we have also been looking on what happens if you have a pulsed signal or a pulse on your cables, especially in terms of inrush current. Yeah, if you run a motor where the current can reach up to 6 times the nominal current. So what's happening there? Should I really have to use the biggest connector to cover this, or can I still run the same thing with a smaller connector, because it's only over a small time? So rely on this application note, find it directly on our website, and yeah, hopefully that this information was helpful for you. So.
Yeah, so Götz, thank you very much for your interesting presentation. As you already said, now we would like to turn our attention to your questions. I see there are not so many questions already inside, so if you search for the question and answer tool, it's on the lower right hand side of WebEx, and there you can send us directly your questions. One question is already in. It's about the slides, if they are available afterwards. And yeah, of course they will be. We will send you a link to the presentation as well as to the recording after or in the next few days. So
besides of that, I can add, for example, we are out in the field as field application engineers, and we are delighted to visit you on your local point. And we also have the possibility to run a kind of seminar with your staff, yeah, and whenever somebody is close to you. Yeah.
Okay, thank you very much. So now I can see there are some questions coming in. Yeah. Götz, maybe we will start with that one. Are there any differences between solid or strained?
At the end, the only thing that counts is the cross section, and this is what is leading the heat away. As long as the cross section is the same, you can dissipate the same heat with that. Yeah. It's different if you have higher frequencies, then some other points may take place here.
Okay. Perfect. Thank you very much. Yeah, there was just a adding of that at the same. So yeah, then as you answered already. So then next question. Maybe I missed it, but what about parallel contacts and maximum current?
Okay, you maybe mean to split, if you have a connector which is limited and you want to split, for example, the total power over two connectors. Of course, this is done frequently, and you can use that. The only thing you should bear in mind is that maybe there is a slight, or there will be for sure a small difference between the contact resistance per contact. So one of them will be has to carry a bit more, and one has to carry a bit less. So don't do it just 50-50. Yeah, just leave the headroom there, and then you're safe.
Okay, then thank you very much. So then we would come to the last question. Indeed, could there be a thermal runaway?
Thermal runaway? Maybe I don't really understand the question. A thermal runaway means that, like in the picture that we see here, if the box is closed and it's heating up like infinite, then of course you will end up with a picture like that. So if you don't care for the heat dissipation, then of course your system will run through the roof.
Okay, so yeah, that's then we are at the end of our webinar. Thank you very much for your time.
Thanks for being here.
Yeah, it was a pleasure.
Supporting me.
Thank you very much for your attention, and I hope we will hear you again, maybe also at the Digital V-Days. They will be in October, and you will find them also on our homepage. And yeah, if you have any questions left after this webinar, just email us at webinarteam@we-online.com. So yeah, I think we will just, it's the next, yeah, you will see our email addresses here. So then, thank you very much. Have a good time. Take care and see you next time. Bye.
Thank you.